Hello folks, and welcome to this lesson on VSEPR theory, part 1. By the end of this lesson, you should be able to predict the electron domain geometry and the molecular geometry for species with up to 4 electron domains. Now, as you've been going through your chemistry education, you might have had some teachers who insisted on drawing water this way, rather than having the hydrogens opposite of each other, or so on and so forth. Well, there's a reason for that, and that reason is going to be explained through this lesson. The VSEPR in VSEPR theory is an acronym, which is why it looks like it's spelled so funny and it doesn't really look like a word. The VSEPR stands for valence shell electron pair repulsion. And it's when you're looking at a molecule and looking at a particular atom and what's surrounding it, and you see that all of the electron pairs that are around this central atom are going to repel each other and move as far away from each other as possible. Before we go into what the shapes and angles and so on and so forth are going to be, let's go through a few definitions. The first one is going to be central atom. This is the atom in the center that you are interested in terms of the shapes that it and its surroundings will form. I'm going to use a symbol for A for this, but in all honesty, if you don't remember this A or the other symbols that I use, don't worry about it. You also have bonding pair or bonding pairs. This is where you have electron pair or pairs between two different atoms. So there's a covalent bond between them. We also have non-bonding pairs. So there is an electron pair, but there's no bond. So an electron pair that has no bond, that is going to be a lone pair. The next bit is electron domain, and this is how many bonding pairs and or non-bonding pairs are around that central atom. So take this molecule, for example. If we're going to define central atom, technically it could be any one of these three, but considering there isn't anything other than one other species around most of these, you're probably only going to be looking at that carbon as your central atom. It's the most interesting thing here. So, in terms of the things that are around it, where you have to look for bonding pairs and non-bonding pairs, this is a bonding pair, and this is also a bonding pair. The carbon does not have any lone pairs around it, so this carbon does not have any non-bonding pairs. In terms of the electron domains, this carbon has 2 electron domains around it. Yes, this is a triple bond, but it doesn't count for more. There are 2 places at which there are electrons grouped around this carbon, and so there are 2 electron domains. If we look at a slightly more complicated molecule, there are several different atoms that could count as a central atom. So this one has a bunch of stuff around it, so does this carbon, that oxygen as well. And so if you're being asked for geometry in this particular atom, you have to look at a specific one. You will either be told this, or you're doing some other investigation and you will know which one you need to be looking at. If we were going to take this oxygen as a central atom, you can see that there are 2 bonding pairs. And this oxygen also has 2 non-bonding pairs. It has 2 lone pairs. And so as a result, it has 4 electron domains around it. So let's start looking at shapes. The first one we're going to look at is going to be AX2, so 2 bonding pairs around a central atom. Examples of this are going to be things like BCl2 or CO2. If we were going to draw the Lewis diagram for BCl2, it would look like this. Remember that beryllium is one of those exceptions. Based on formal charges, it's only going to have 4 electrons on the outside and not go all the way up to 8. So let's take this, and if we were going to look at how far you can take these 2 pairs of electrons apart, well, you want it to be in a straight line. 180 degrees is the farthest away these electron domains can be from each other. So you take a central atom, have two terminal atoms around it, and then spread them apart as far as possible. Well, you get a straight line. For your structural diagram, what you're basically going to do is you're going to draw a picture where you're just interested in the structure. So you're not going to draw any double bonds, anything on the terminal, any lone pairs on the terminal atoms, you're not going to draw either, and then we're left with that. So, if we're going to name this shape, I would hope that it makes sense that this shape would be referred to as linear. It's a line. And the angle, the bond angle, refers to the angle between going from one terminal atom to the central atom and then to another terminal atom. So if we're looking at this angle, there is 180 degrees between it, and so that's the bond angle. For AX3, you have 3 bonding pairs. Examples of this would be BF3. So if we were going to draw the Lewis diagram, B boron is another one of those exceptions. You're going to draw the fluorines around it. It doesn't go all the way up to 8. So if we were going to take all these fluorines and spread them apart as far as possible, you can see that you get this sort of a shape. It is flat, so it is all in one plane, and it is triangular. When you're drawing the structural diagram, that's basically what you're going to be drawing. Hopefully, it is not a surprise that the name of this geometry shape is trigonal planar. And as you can see, the bond angles are going to be 120 degrees. So we're looking at this angle, and this angle to make them as far apart as each other. All of these angles are going to be 120 degrees. At this point, we're going to start bringing in some lone pairs. So the example that we're going to use is SO2, and if you draw the Lewis diagram, you're going to get something like this. Yes, this has a resonance structure, but the resonance structure doesn't actually change how many electron domains or anything else, and so we're just going to draw the one structure. So if you take a look, we are still starting with that trigonal planar 3 electron domain shape. So we are still starting with this sort of a shape. However, your lone pairs, as just electrons, are basically invisible. So instead of having this whole shape and seeing every part of it, you are going to have basically this. So you have this central atom, you have the 2 terminal atoms, and they're not in a straight line, but they are in a bent line. When you're drawing the structural diagram, you may ignore what's going on with your terminal atoms, but you are going to draw in lone pairs that are at your central atom to refer to the fact that they are there. They're invisible, but it's there. So the name of this shape that you can see is referred to as bent. It's a bent line. In terms of the angles, the one that you're going to be interested in is this one, the one where you can actually see things going on. So from the oxygen to the sulfur to the other oxygen. This shape is still based off of that original trigonal planar shape, it's just that part of it is invisible. The angle, therefore, is going to be close to that 120 degrees, but it's not quite 120 degrees. It's a little smaller. That's because lone pairs have greater repelling power. And so instead of it being 120 degrees evenly, these bonding pairs get pushed closer together by that lone pair. And so it is going to be a little bit closer than that 120 degrees. With the other shapes that we looked at, the electron domain geometry and the molecular geometry were the same. However, in this case, the electron domain geometry is based on having 3 places of electrons worth. So the electron domain geometry for this particular shape is trigonal planar. The name of the molecular geometry, so the name of the shape that you can see, is bent. So there is a difference between the electron domain geometry and the molecular geometry once you start putting in electron pairs or lone pairs. From here, we're going to go to 4 terminal atoms, so you have 4 electron domains. A very simple example of this is going to be CH4, and you have your Lewis diagram where you have your carbon, you have your hydrogens around it, the end. Now, in terms of what this shape is going to look like, based on paper, what you can see when you draw it on paper, and based on what you've seen before, you might think that you're going to have this flat shape with 90-degree angles everywhere. However, this is not actually the case. This is the shape that you get when you have 4 electron domains. So you can see that it doesn't fall flat. It's not a flat shape. It is rather 3-dimensional. And if you know your dice, you can know that this shape is referred to as a tetrahedron. If you think of these places where the atoms are as corners and then you draw planes around them, you have a triangular base and then you have triangles coming up to form a pyramid-like shape. The reason that you get this sort of a shape rather than that flat 90-degree angle split between all of your different atoms is because if you take a look and take advantage of the fact that we do live in 3-dimensional shape, the bond angles that you get are bigger than 90 degrees. In fact, these are 109.5 degrees, and that's generally going to be the same as long as all of these are equal to each other, or as in all of these are bonding pairs, and it's going to be 109.5 degrees, evenly spaced out, no matter which terminal central atom terminal pair you're looking at, or set you're looking at. Drawing this structure can be a little bit more complicated because how do you take that 3-dimensional shape into account? Well, the thing is that you generally are going to take 2 of them and say that they are in one plane. So we're going to be taking this central one and these 2 over here, and we are going to say that they are on the same plane. So this is flat. This is your paper. Now, as you can see, one of the hydrogens is going further away from you, sort of into where the paper would be, and one of them is coming towards you. So it's coming out of the page towards you. When you draw these, you are going to use what we call wedges and dashes. Dashes are what you use to draw things that are going into the paper, so further into the paper, away from you compared to this plane. So that would be this red one. And then you would use wedges for things that are coming out of the page towards you. You'll see this notation being used quite a few other times, both within this and the next lesson, and also in the organic chemistry unit. From here, as I mentioned, the name of the molecular geometry is tetrahedral, and therefore the name of the electron domain geometry is also tetrahedral, and the bond angle is 109.5 degrees for all of these. Now let's start bringing some electron pairs, some lone pairs into this whole tetrahedral electron geometry. An example is going to be NH3. So for NH3, you can see that you have 4 electron domains. And so when we are looking at the model itself, we're going to start with that tetrahedral shape. So the electron domain geometry is still going to be tetrahedral. However, there is one lone pair which is basically invisible. When you have that, you can see that you can still see your central atom, you still see your terminal ones. This looks very similar to what you saw before, but it does have a different shape, name of the shape, and so on and so forth. So let's start drawing and looking at what those differences are. There's no good way to really draw a lone pair using wedges or dashes, so we're going to use that lone pair in that plane with this particular hydrogen, and then we have one hydrogen coming towards you and then the other going away from you. So towards you, away from you. So if you take a look, it very much looks like a pyramid. It has a triangular base, and that's why the name of this shape is going to be trigonal pyramidal. In terms of the angles, we're not going to be looking at any angles involving this particular lone pair, because remember, it's invisible. So we're going to be going from terminal, central, terminal, and all of these are going to be pretty much the same from each other. However, it's not going to be 109.5 degrees because you have that lone pair. It pushes everything closer together, and so this shape is going to crowd a little bit more on the bottom. And so the angle that you get is closer to 107 degrees. The last shape that we're going to be looking at will have 2 bonding pairs and 2 non-bonding pairs, and here is that water example. So when you draw your Lewis diagram, I'm going to go with the tried and true, and let's take a look at what this looks like with our structure. So it still has 4 electron domains, so the electron domain geometry is still going to be tetrahedral, but because of the fact that we have 2 lone pairs, 2 of these are going to be invisible. So, I mean, yes, if you look at it at a certain angle, you are going to see that it does look like a straight line, but in reality, when it comes to things that count, and this is going to come into play when we talk about molecular polarity, this is really a bent line. So, when you have your tetrahedral shape with 2 bonding pairs and 2 non-bonding pairs, 2 lone pairs, the shape is going to be bent. Now, in terms of the angle, there's only one angle that we're interested in. Based off of that tetrahedral shape, you're going to start thinking at 109.5 degrees, but we have 2 lone pairs, and so everything is going to come a little closer to each other. So it's going to not be 109.5, it's going to be even smaller than that 107 degrees. This ends up being 104.5 degrees. In this particular case, when drawing the structural diagram, I'm not really going to bother with wedges and dashes. You only have 3 things that are actually going to be visible. Draw them at a bit of an angle and not in a straight line to emphasize that whole bent shape. That really matters, as I've mentioned before, and then you can draw in the other 2 lone pairs. So again, the name of the molecular geometry is bent, so there is some overlap between some of these names, but that's okay. The important thing is that you remember that the angles are different. The angle in this bent shape is 104.5 degrees. Don't forget that the other bent shape that we saw with 3 electron domains, the bond angle is 117 degrees. The minute details of those bond angles are important for you to memorize. So, those are all the shapes for all the possible molecular shapes that you can get up to 4 electron domains. That's the end of this lesson. I'll see you next time.